Now we have a path difference problem. We have Susie Soundlover standing between two speakers. Let's call them speakers 1 and speaker 2. The two speakers are separated by 6.5 meters. And Susie is 2.5 meters from this speaker right here. The two speakers are emitting the same tone of frequency, 686 hertz. I'm going to say that these tones are in phase. Does she hear a loud sound or no sound, and support your answer? So when we're talking about path difference problems, we're talking about constructive and destructive interference. We should always begin these problems for writing down our conditions. So if we're in phase, we get loud sound when we have constructive interference. And that happens when our path difference delta D, and we'll put up here, delta D is the difference between D2 and D1, when our path difference is an integer multiple of the wavelength. So n lambda, where n is 0, 1, 2, and so on. We get no sound or quiet sound when we have destructive interference. For destructive interference, delta D is a half multiple of the wavelength, which we write as n lambda over 2, and n is an odd integer. So what we're going to have to do here is let's find the wavelength. Let's find the path difference where Susie is standing. Let's figure out what is delta D over lambda, and let's see, does that fit constructive or destructive interference? So when we have loud sound or constructive, we see that delta D over lambda is going to give us an integer. It's going to give us n. When we have destructive interference or no sound, we find that delta D divided by lambda is n over 2. So it's going to be 1 over 2, 3 over 2, 5 over 2, and so on. So is delta D over lambda an integer or a half an integer? Okay, so let's get to work finding delta D. The first thing we should do is let's draw D1 and D2. D1 is the distance between Susie and speaker 1. There's D1, so I see that my D1 is 2.5 meters. D2 is my distance between Susie and speaker 2. I have to do a calculation to find my D2. What I notice is that if I add D1 to D2, I get the whole distance between the speakers, 6.5 meters. So D1 plus D2 equals 6.50 meters. That means D2 equals 6.5 meters. Subtract D1, which was 2.5 meters, gives us 4 meters. Now I can find my path difference delta D. 4 meters, subtract 2.5 meters. I'll keep writing in the absolute value signs even though I don't really need it. So my delta D then, 4 meters subtract 2.5 meters is 1.5 meters. All right, there's my delta D. Next I need to find my lambda. I have my frequency, so it's not going to be difficult to find my lambda. So V equals F times lambda. That tells us that lambda is V divided by F. The problem doesn't say anything about temperature, so we're going to go ahead and assume that V is 343. Divided by our frequency of 686 hertz. 343 over 686 is 0.5 meters. Okay, I've got my lambda, I've got my delta D. I am all set now to do my comparison. Delta D divided by lambda is 1.50 meters divided by 0.5 meters. 1.5 over 0.5, that gives us 3. So we see that delta D over lambda matches our condition for loud sound or constructive interference with n equals 3. we have delta D equals 3 times lambda, and that gives us loud sound or constructive interference. Okay, and then this is a typical way to solve these problems. Even if you change the geometry, you don't change the approach. Okay, let's do another one that could be a little bit complicated, but it's not a different problem overall. It's the same kind of problem, it's just a new geometry. So in this problem, part A, we'll do this quickly because we took our time with the Susie problem. State the conditions for constructive and destructive interference. Then I'm going to add for sound sources in phase. During this year, we only discussed sound sources in phase in 2006, so that's what I'll put in brackets here. This year, since we've done both, I would specify if it was in phase or out of phase. So for constructive, I don't have tons of room, and I do have a big marker, so I'll write C for constructive. Delta D, the path length difference, equals n times lambda, where n is an integer. And for destructive, delta D equals n lambda over 2, where n is an odd integer. And then at the end, I'll put in the reminder that delta D is the path difference, D2 minus D1. If I had more room, I would write out the words constructive and destructive, and I would indicate that constructive interference refers to loud sound, and destructive interference refers to quiet sound or no sound. Okay, now on to the calculation part of the problem. We have a hamster standing in a rectangular tunnel, so I've got 0.8 meters here, 1.2 here, 0.8 here, and 1.2 here. A speaker sits in one corner, and the hamster is at the end of the corridor as shown. The speed of sound is 343 meters per second. What is the lowest frequency for which the hamster hears no sound? So just by the way the question is posed, that tells us that this is an interference problem. So we're going to have to apply our conditions. The question says hears no sound, so we know right off the bat we're talking about destructive interference. So no sound means destructive. So let's write down our condition. Delta D, which is going to be D2, subtract D1, equals n lambda over 2, where n is any odd integer. Okay, now we've got to start narrowing some things down. Let's deal with n first. The problem says, what's the lowest frequency? That tells us to choose n equals 1. No sound, that's our destructive. We've got that taken care of. So now we know that delta D, which is D2, subtract D1, is going to be lambda over 2. This equation tells us about lambda. We know that we want frequency, so we're also going to have to use V equals F lambda. After we sort out our lambda, we'll use this equation and find our frequency. Okay, so now we've got some ideas. The next thing we've really got to figure out is what is D1 and what is D2. Here we have to remember the definition of what D is. D2 is our distance between the hamster and the second sound source. D1 is the distance between the hamster and the first sound source. So let's think about what's happening. Sound comes out of the speaker and the sound splits. Some of the sound comes straight down. So this is one path that the sound takes, but it's not the only path that the sound takes. Some of the sound also goes down this part, comes around this way, back around the corner this way. Now we've got two paths. I'm going to call this path D1, and I'm going to call this path D2. I can use the geometry here to figure out my D1 and D2. After I've got that figured out, I can calculate my delta D. So D1's not too tough. It's just straight down this length, and we're given that that length is equal to 120 centimeters. So D1 is 1.20 meters, and I'm going to go ahead and put it in meters. Our D2, that's a little different, so I have to come down this corridor. That's 80 centimeters long, so it's 0.80 meters. Then I have to come down this part, that's 1.2 meters. Then I have to go all the way down this part, that's another 0.8 meters. So my path length, D2, is 0.8 plus 1.2 plus 0.8. D2 equals 2.8 meters. Now I can find my delta D. Delta D equals the difference between D2 and D1 equals 2.8 meters, subtract 1.2 meters. 2.8 take away 1.2 is 1.6 meters. Okay, I know delta D. This means I can find my lambda. So delta D equals lambda over 2. That means lambda equals twice delta D, 2 times 1.6 meters. My lambda is 3.2 meters. Okay, almost done. We were asked to find the frequency. We've got the wavelength found. Now we need to find the frequency. So V equals F lambda. That means F is V divided by lambda, 343 meters per second. We were told to use that for our speed. Divide by 3.20 meters gives us a frequency of 107 hertz. Okay, there's the first part. We did lots of work there. The second part, we're really kind of ramping it up a notch. In the second part, we set the speaker to a frequency of 1005 hertz. That means we can find the wavelength. How far does the hamster have to move to the left? So our hamster is going to scurry over here to hear no sound. So we have to repeat our problem, but the hamster is not sitting here anymore. This hamster is over here. We still have to have destructive interference, and this time we know the wavelength. Okay, let's draw a new picture, because I think a new picture is going to take us a long way in this problem. So I'll grab a fresh sheet of paper, and we'll redraw our system. I don't know how well I can draw a hamster, but probably just be a little stickman hamster. So here's our tunnel. Let's put our hamster right here. Oh my goodness, I don't know what a hamster looks like. There's a tail, there's some ears, and it kind of looks like a rabbit, sorry. And let's put our speaker in. Here's our speaker emitting the sound. And what we know now is that our frequency is 1005 hertz. That means our wavelength lambda is going to be V divided by the frequency, 343 meters per second, divided by 1005 hertz. Gives us a wavelength of 0.341 meters. All right, we've got our wavelength. We know we still have to deal with our condition for destructive interference, but let's sort of nail down our geometry first. So our hamster has moved to the left a ways. I'm going to call that distance x. I'm going to draw in my D1 and my D2 just like I did last time because I know I care about the path. My D1, we've got to come all the way down this corridor, and then we have to come over here. So my length D1 is going to be 1.2 meters plus x. Okay, so D1 is not so bad. Next I have to find my D2. So let me draw my D2. D2 comes down this hallway, that's 0.8. Comes down this hallway, that's 1.2. And then comes a little way down this hallway. So then D2 is going to be the length down here, 0.8 meters, plus the length down here, 1.20 meters, plus the length down here. Now then this one, not exactly tricky, but we do have to put some thought into it. If our length here is 0.8 and our length here is x, then this little bit of length must be 0.8 minus x. Okay, hopefully that makes sense. So path D2 only comes down this far, so it comes this little bit of a ways down here. This little bit of a ways is the whole length, take away that bit of length. So then our D2 is 0.8 plus 1.2 plus 0.8, 2.80, subtract x. Okay, let's get into our conditions for constructive and destructive. Let's calculate our path difference. So we know our path difference, delta d, is equal to d2 subtract d1, which is going to be 2.80 meters subtract x, subtract 1.20 meters plus x. Okay, this is a little confusing with all those brackets. Let me try and simplify that. So I've got 2.8 meters subtract x minus 1.2 meters minus x. Got to be careful with those minus signs there. So 2.8 take away 1.2, that's 1.6. Minus x is minus 2x. And I know that this whole thing is going to be positive, so I'm just going to drop those absolute value signs. Okay, there's my delta D. Next, I've got to put it together with my conditions for destructive interference. So for destructive interference, I know that I have to have, because we want our hamster to hear no sound, so I know I need delta D equals n times lambda divided by 2. I'm not quite sure about n yet. I'm just going to leave that as n because I don't really know what value to put in there. I do, however, know what to put in for my lambda. My lambda is 0.341 meters. So then my delta D is n lambda over 2, n times 0.341 over 2 equals n times 0.1705 meters. All right, now let's put in what I sorted out for my delta D, which is 1.6 minus 2x. I'd like to solve for my x, so let's get x on a side by itself and everything else on the other side. So then 2x is equal to 1.60 meters, subtract n times 0.1705 meters. I'm going to divide everything by 2. X is 1.60 meters, subtract n times 0.1705 meters, divided by 2. I think I'll go ahead and simplify that. 8525 meters. Okay, now I'm just going to try n equals 1 and see what I get. So if n equals 1, x equals, oh my goodness, I did 0.6, 1.6 divided by 2 and I got 1.6. That should be 0.8, shouldn't it? Okay, that looks better. So I get 0.8 minus 0.08525 to get 0.715 meters. So this tells me that if my hamster moves 71.5 centimeters to the left, this is where he'll hear no sound, and that's the furthest he can move because this is only 80 centimeters long. If n gets bigger, he exceeds the length of the tube. So that's how far the hamster has to move to get at a place where there's destructive interference.